Hello again, this is Professor Roman. Welcome back to the lecture series called Transition to Advanced Mathematics. We're talking about logic. We talked about truth tables. Now, it happens that some statements that look quite dissimilar actually have the same logical meaning. So let me give you an example. Consider the conditional, P implies Q, and the statement not P or Q. We can draw the truth tables for both of these statements in one big table. Here are the columns for P and Q, and I reproduced them here just for convenience. This is the implication, P implies Q. Here's a temporary or intermediate column, not P, and here is not P or Q. If you compare the P implies Q column and the not P or Q column, you will see they are the same. In other words, these two statements have the same truth value in all cases. If one is true, the other is true. If one is false, the other is false. That calls for a definition. Two statements, A and B, are logically equivalent, sometimes just called equivalent, if they have the same truth value for all possible values of the simple statements or variables contained in those statements. If the statements are in English, we're talking about the simple statements. If the statements are in symbolic form, we're talking about the variables. The notation I'm going to use for logical equivalence looks like this. It's an equal sign with an extra bar. And this would be read A is logically equivalent to B. So we can write P implies Q is logically equivalent to not P or Q. They have the same logical meaning. So as an example, the statement x not equal to 1 or y equal to 2 is logically equivalent to x equals 1 implies y equals 2. As we saw in this example, in a sense, it's very easy to tell whether two statements are logically equivalent because it's not that difficult to compute truth tables. So all you have to do is compare the truth tables. One of the most important aspects of logical equivalence is that if you have a statement in an argument, you can replace that statement with any other statement that's logically equivalent to it, and you will not affect the validity of the argument. And we'll see some examples of that when we start talking about valid arguments. Okay. You can always substitute a logically equivalent statement at any point in an argument. There are some logical equivalences that are very important and need to be committed to memory. Fortunately, many of these are analogous to properties of arithmetic, so shouldn't be a problem remembering them. First, a quick definition. An operation that, informally speaking, cancels itself, that if you apply it twice, it's as though you didn't apply it at all, is called an involution. So for example, taking the negative of a real number is an involution. If you take the negative twice, you get back to the number you started with. Taking a multiplicative inverse of a non-zero number is also an involution. Taking the complement of a set is an involution. The complement of the complement of A is just A. Now, here are some important examples of logical equivalence. P, Q, and R are statements. The following holds. Negation is an involution. That is, if you apply negation twice. Now, this is a little different situation. You don't recover P itself, but you get something logically equivalent to P. And so we kind of fudge the terminology a little and call this an involution anyway. The commutative laws hold for conjunction and disjunction. P and Q is logically equivalent to Q and P, and similarly for the disjunction. The associative laws hold. If you first take P and Q and then follow that by conjunction with R, you could instead have first taken Q and R and preceded that by conjunction with P. And similarly for disjunction. The distributive laws hold. You can distribute a conjunction across a disjunction and vice versa, and it looks like this. So these three properties have exact analogs for arithmetic, or addition and multiplication. The last property, however, does not, and it is called, there are actually two equivalences here. They're called De Morgan's laws. They're very important, used quite often. The negation of P and Q is not P or not Q. The negation of P and Q, P or Q is not P and not Q. So what's going on here is if you want to distribute the negation inside a conjunction, you can do so, but you have to change conjunction to disjunction. You have to change and to or. You have to change or to and. It's surprising how many people don't have a grasp on this. If you watch the news, for example, every once in a while, a so-called pundit, a political pundit or whoever, expert on something, will make a mistake and will say, not P and Q. And then they'll say, in other words, not P and not Q, where it should have been or not Q. So these laws are something you need to think about until it makes sense to you. You can draw the truth tables and see that they're logically equivalent, but they're vitally important. We use them all the time, so you need to know them. Okay. Example, all my students are interested in logic, but not all my students are interested in geography. Of course, but here has the same meaning as and. This is a conjunction. Symbolic form looks like this, P and not Q. If we want to negate, we can start by just sticking a negation sign with parentheses in front of everything. We then use De Morgan's law. This is equivalent to this, not P or not Q. Now we can use the fact that negation is an involution, and we end up with not P or Q. Translating back to English, not all of my students are interested in logic, or, and that's the key here, this and has switched to or, all of my students are interested in geography. 216, by the way, this expression here, is logically equivalent to P implies Q. We did that as our first example of logical equivalence, which means that this statement is logically equivalent to if all my students are interested in logic, then all my students are interested in philosophy, in geography. Okay. So if you should read over these sentences. All my students are interested in logic, but not all of my students are interested in geography. If you need the negation of such a statement, it is, well, there are two possibilities. One is if all my students are interested in logic, then all my students are interested in geography. Now, when you read these two statements, they don't look like negations of each other. So this is a good example of the power of the techniques we're developing, symbolic form and the use of logical equivalence, in this particular case, De Morgan's laws, to be able to get from here to here and know that even though this doesn't seem intuitively like we have the negation, we know that we do have the negation. And so it's up to us to just accept it, but hopefully to stare at it long enough to see the connection, if possible. Okay? So this should be a good example of why these techniques of symbolic form and logical equivalence are useful. Okay. The conditional statement has some important relatives, and they are listed in the following definition. P and Q are statements. The converse of P implies Q is Q implies P. Just reverse the antecedent and the consequent. The contrapositive of P implies Q is not Q implies not P. So not only do we swap the antecedent and the consequent, but we negate both of them. The inverse of P implies Q is the statement not P implies not Q. So here we don't swap the antecedent and consequent, but we do put negations. These are the terms you definitely need to know. Here's an example. The original statement is, if it is raining, then I carry an umbrella. Converse, if I carry an umbrella, then it is raining. Inverse, if it is not raining, then I do not carry an umbrella. Contrapositive, if I do not carry an umbrella, then it is not raining. Let's pause for a minute and review these sentences to see if we can tell which, if any, are logically equivalent. If it's raining, then I carry an umbrella. Is that logically equivalent to if I carry an umbrella, then it's raining? No. Because the statement may be true, but a person can still carry an umbrella for other reasons. Self-defense, style, whatever. Or they think it's going to rain, but it hasn't rained. So these are not necessarily true at the same time. One can be true, the other can be false. So these are not logically equivalent. But look at the statement and its contrapositive. If it is raining, then I carry an umbrella. That's a positive assertion. If it rains, I will carry an umbrella. Therefore, if I don't carry an umbrella, it can't be raining. A statement and its contrapositive are logically equivalent, but a statement and its converse are not. Now all that is fine, but I haven't really proven it until I draw a truth table. At P, at Q, not P, not Q, here are the four relatives of the conditional. P implies Q, Q implies P, and so on. All you have to do is look at the columns. This is the conditional and this is the contrapositive. True, true, false, true, 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 false, true. These are the same, have the same truth value at all times. So they are logically equivalent. Conditional and converse are not logically equivalent. If you look at these two intermediate rows, you will see that we have different values. The converse and inverse are logically equivalent. So these come in logically equivalent pairs. Conditional, contrapositive, converse, inverse. And there will be times, as I mentioned before, that in the construction of a valid argument, you can replace any statement by a logically equivalent statement. This is particularly useful to replace a conditional by its contrapositive, and that's something we will do frequently. If we want to prove a conditional, P implies Q, it's just as good to prove the contrapositive, not Q implies not P, and sometimes that's easier to do. Consider this statement, P implies P or Q. We talked about this statement earlier, and we said that certainly looks like it ought to be true all the time. Here's the truth table, and sure enough, the final column is all truths. A statement such as this, which is always true, is called a tautology. This statement, as an example, has this truth table, and it's all false. Statements that are always false are called contradictions. Here's the formal definition. A statement that is always true, regardless of what truth values are assigned to the variables, or simple statements, that make it up is called a tautology. Another way to say something's a tautology is to say that it's logically true. This means that the statement is true by virtue of its structure. Meaning is irrelevant. P implies P is about one of the simplest tautologies, and it's just true because of the structure. It doesn't matter what P is. It is important to understand the difference between a statement that's logically true, a tautology, and a statement that's merely true, let's say. For example, today is Friday and it is raining is not logically true because there are times when it is false. But on a rainy Friday, it is true. So it's not a tautology, but it is on occasion true. On the other hand, the statement today is Friday or today is not Friday, this is always true. It's not true sometimes and false other times. So it is a tautology. Since symbolic form plays such a prominent role in exposing the logical structure of a statement or an argument, we should probably spend a little more time trying to define more precisely what constitutes a legal statement written in symbolic form. You can't just throw some symbols down, variables and connectives, and expect it to be a legal symbolic form statement. So you have to be careful how you construct it. An expression like this, P and Q in parentheses, or not R and S in parentheses, is a legal statement. But an expression like this, P and Q or R, is not legal because it has an ambiguous logical structure. The problem here is we've got two operations going on here, and we can do them in either order. We could do the conjunction first and then the disjunction, or vice versa. There's no indication here as to which operation should be done first. And if you construct a truth table for the two options, the two possibilities, here we do the conjunction first, then we do the disjunction. Here we do the disjunction first and then the conjunction. Look at the two columns, they're not the same. So without the parentheses, we have an ambiguous situation, and therefore we don't have a legal statement. So how do we know exactly which symbolic expressions are legal statements in the propositional calculus? Well, the answer is we need a formal definition, or in fact, two formal definitions. So here's what they are. First, we have to define the language of propositional calculus. This is the symbolic language. Obviously, in a way, English, any written language can be used to express the concepts of propositional calculus, but we're looking at the symbolic expressions. So the language of propositional calculus consists of the following: enclosures, parentheses. Oftentimes, those are the only ones used. I extended the definition here a little bit to be able to use brackets or braces. It's just convenient. It makes things easier to read, but it's not, strictly speaking, necessary. You've got to have at least one set of enclosures. Variables. And when there's a lot of variables, it's better to use a single letter and subscript them. And the 5 basic connectives. So the language is very restricted. Enclosures, symbols for variables, and symbols for the 5 basic connectives. Using the formal language, we can define the expressions that are legal statements in the propositional calculus, and they are called well-formed formulas. So this is not well-formed because of the ambiguity. Both of these are well-formed. Here's the definition of a well-formed formula, which often gets abbreviated WFF. Any variable, all by itself, is a well-formed formula. If I write P, there's no ambiguity. I've just written P. If you have two well-formed formulas, W and V, then each of these is also a well-formed formula, not W in parentheses. We have conjunction, disjunction, implication, biconditional, but there are parentheses around all of them. Now you may be looking at this saying, well, what do you need parentheses around these for? And on the outside, nobody ever writes 5 plus 3 with parentheses and they're done. You don't need the parentheses. Well, we need the parentheses because these form the building blocks for bigger well-formed formulas. And if you start dropping the outer parentheses, you run into these kinds of problems. When you're done using these two statements here to construct a well-formed formula, when you're finished, you can take off the outer parentheses. But you may have used number 2 here several times. You can't remove any of the other parentheses. Okay? So let me just finish this. Moreover, an expression, this is omega, common symbol for a well-formed formula, is a well-formed formula if and only if it can be obtained by applying a finite number of constructions of this form here, starting with one or more variables. And this is what is referred to in computer science as an inductive definition. It tells you how to build things one step at a time. So as we've seen, this is not a well-formed formula. And the reason is that you cannot construct this by following the definition. You can start with P, you can start with Q, you can start with R. Those are variables. So they're well-formed formulas by themselves, but when you start to assemble them, if you want to do P and Q, you have to put parentheses. So whichever connective you decide to do first is going to require that extra parentheses, and so you're going to end up with one of these two. You're not going to end up with this. Here's a more complicated expression. We would like to know, is this well-formed? Is it a well-formed formula? Well, here are the steps to construct it. P and Q are by themselves well-formed formulas, and so this is also P and Q with the parentheses. You must keep the parentheses. R is a well-formed formula, therefore so is not R with parentheses. Not R and S are well-formed formulas, therefore their conjunction is, again, with outer parentheses. Now we can take this well-formed formula and this one, and we can take their disjunction, again with outer parentheses. Now we can remove the outermost and only the outermost enclosures, and it'll look like this. It is somewhat customary also to drop the parentheses around the negation and drop it to this. This is okay. The reason it's okay is because negation is always done first. When you look at a well-formed formula, the negations are done first. So there's no ambiguity here. You would do not R first before you took the conjunction with S. This would never be the negation of R and S. It's the negation of R and S. Okay, if that made any sense. There is an operator precedence throughout the list of connectives, and this is what it is. You always do negation first, conjunction comes second, disjunction third, implication, conditional, and then biconditional. So if you follow the operator precedence, this becomes well-formed in the sense that you have to do the conjunction first. So it becomes this. Now, in my classes, I always tell the students, do not use operator precedence ever. Always put in enough parentheses, braces, brackets to disambiguate your sentences. This is for your protection and for mine, because I have had students who will write something like this without the parentheses, and when the intention, the correct answer was the other way around, P and Q or R like this, and they'll say, well, I knew what it was supposed to be. And I say, well, I'm sorry, but you didn't write it correctly. You relied on operator precedence and you made a mistake. It's just not worth getting into that. So in my classes, I do not allow students to rely on operator precedence. It's just, how should we say, a little bit dangerous. Okay, so you must include sufficient parentheses, braces, and brackets so that if someone reads what you wrote and that someone has no idea about operator precedence, they will not be confused. Okay. Okay, we are now ready to discuss the issue of how to tell whether a given argument is valid or not. Loosely speaking, an argument is just a sequence of sentences or statements that are called the premises or hypotheses of the argument, followed by another statement called the conclusion of the argument. And the idea, of course, is that the conclusion is supposed to follow logically from the hypotheses. And that's what we mean by a valid argument. So here is a more precise definition. An argument is a sequence of statements, usually written when it's convenient in one horizontal line. But if the sentences or statements are long, we write it in a vertical format like this. The statements A1 through AN are called the premises or hypotheses of the argument, and the statement A is called the conclusion of the argument. We've got two symbols here, the 3-dot symbol and the horizontal line. They both stand for the word therefore. So, for example, here is an argument we have discussed before, or something similar. If today is a holiday, then I can go to the beach. Today is a holiday, therefore I can go to the beach. So we have two hypotheses and one conclusion. An argument is valid if, whenever the premises are true, so is the conclusion. Otherwise, the argument is said to be invalid. Now, it's important to notice that even though an argument is not of much use if one or more of the hypotheses is false, according to the definition, we don't require that they all be true. So, for example, 1 plus 1 equals 3, therefore 1 plus 2 equals 4. One hypothesis, one conclusion. This is a valid argument because if the hypothesis is true, then the conclusion is true. But again, because the hypothesis is not valid, one would reasonably argue that this is not a useful argument, even though it is a valid argument. Yeah, for all we know, there's another planet where 1 plus 1 is equal to 3. And so on that planet, this would not only be a valid argument, but would lead to a valid conclusion. So, according to the definition, To determine whether an argument is valid, we need only consider the cases where all of the premises are true. Determining whether an argument is valid or not is usually done simply by constructing a truth table. So it's a straightforward process. The tricky part is in converting the argument to symbolic form, because the hypotheses can get rather complicated, as we'll see. So let's consider this argument again. If today is a holiday, then I can go to the beach. Today is a holiday, therefore I can go to the beach. In symbolic form, it looks like this. P is today is a holiday. Q is I can go to the beach. The argument in symbolic form, P implies Q, P therefore Q. This is, as we've discussed before, modus ponens, and it's one of the most commonly used arguments in debating circles. To see that this is valid, that modus ponens is valid, we construct a truth table. The premise P implies Q, conclusion Q. Now notice that this is not your ordinary table in the sense that the conclusion is not the final column. You just have to construct the truth table so that you get truth values for both hypotheses, in this case, and the conclusion. So this is one way to organize the table. It makes sense. So what I have to do is look at the rows in which both premises are true. So the first row, actually it's literally the third row of the table, the first row of truth values, true, premise true, conclusion true. And that is the only row in which both premises, the first column and the third column, are true. So this is a valid argument. Here's another one. If I study, I won't flunk the next test. I study, therefore I won't flunk the next test. For symbolic form, let P be I study, let Q be I flunk. Careful here. Q is not I won't flunk, because that is a negation to I flunk. So we want, in general, we want the variables to be simple statements. There are exceptions to that, but that's what we generally want. So the symbolic form of this argument is P implies not Q. P, therefore not Q. That's another example of modus ponens. So we don't need to draw the truth table. We know all examples of modus ponens are valid. How about this one? If today is a holiday, then I can go to the beach. I can go to the beach, therefore today is a holiday. So for symbolic form, we have P is today is a holiday, Q is I can go to the beach. The symbolic form is P implies Q, Q therefore P. So this looks similar to modus ponens, but it's not, because this Q needs to be a P in order to have modus ponens, and this P needs to be a Q, so these are reversed. So we draw the truth table, just as we did before. The premise, one of the premises is Q, which is here. The other premise is P implies Q. The conclusion is P. Now, if you look at the rows in which the premises are true, in this row they are both true, and so is the conclusion. But in this row, both premises are true, yet the conclusion is false. Therefore, this argument is invalid. It is not a logical argument. It's not logically valid. Another example, if today is a holiday, then I can go to the beach. If I can go to the beach, then I can take a surfing lesson. Therefore, if today is a holiday, I can take a surfing lesson. So, we'll let P be today is a holiday. Let Q be I can go to the beach. Let R be I can take a surfing lesson. Then this is the symbolic form. P implies Q, Q implies R, therefore P implies R. This should seem valid if you read over the hypotheses and the conclusion a few times. It's a chain effect here. P implies Q, which in turn implies R. So P ought to imply R. But that's not a proof. And sometimes reasoning like that will lead to a false conclusion. So we need the truth table to be absolutely certain that our intuition is accurate. So here is the truth table. We have P, Q, and R. We have the two premises, and we have the conclusion. I've marked with arrows the rows in which both premises are true. And you see that in all cases the conclusion is true. Therefore, this is a valid argument. Let's consider the following argument already in symbolic form. P and Q implies R. P, therefore, R. This should strike you as problematic. This is not a valid argument because you need both P and Q in order to deduce R. And if you just have P, you then don't have enough to deduce R. But let's take a look at the truth table that will tell us for sure one way or the other. So here's the premise P, here's the Q column, here's the other premise. So we have, and here's the conclusion R. So we have to look at the rows in which both premises are true. First column, last column. True, both true. Did I say last column? Yeah. Both true, and that's it. Okay. In these three columns, the conclusion is true, true, but this one is false. So this row has both premises true, but the conclusion false. So this is an invalid argument. The argument that we did in this example 224 here whose symbolic form is P implies Q, Q implies R, therefore P implies R. As I said, that was a chain type argument. So here it is reproduced. This can be generalized very easily. So if we have statements, they can be simple, represented by variables, or compound. It doesn't matter. So S1 through Sn are just statements. An argument that has this chain for hypotheses, S1 implies S2, S2 implies S3, and so on. Each one implies the next one. The conclusion is that the first one implies the last one. This is a very common argument form, perhaps as common as modus ponens. It has a name. The arguments are called sorites. The I is a long I, and the E is a long E. Sorites. They are always valid arguments. And the proof of that would require drawing a truth table and so on. But I'm going to leave that for you to think about. let's consider this argument. A student who studies will not flunk this course. John is very smart. Even smart people must study, therefore John will not flunk this course. This is our first example of an argument where it's not clear what the logical flow is, what the logical structure is. It appears as though the first and second hypotheses have nothing to do with each other, but the second and third are tied in because of smart here and so on. So what we need to do to try to get the symbolic form for an argument that's not so obvious is, I think, one approach in certain cases is to kind of condense the meanings here. Use your knowledge of English to write this in a shorter way that removes some of the confusion. So this is what I wrote, and I'm sure there are other ways. Study implies not flunk. John implies smart. Smart implies study. Therefore, John implies not flunk. So now we can choose the variables. P is study. Q is flunk. R is smart. S is John. And the argument looks like this. P implies not Q. Study, which is, where to go? P, implies not flunk, not Q. P implies not Q. S implies R. John implies smart. Smart implies study, should be R implies P. And the conclusion, John implies not flunk, should be S implies not Q. So that part of the process is being finished. That is in many ways the hard part. We now need to manipulate these symbols to get something that either is an example of an argument we already know is valid, such as modus ponens or a sorites, or construct a truth table. And if you have trouble manipulating the argument to something that looks familiar, you can always do the truth table. That's always a way out, and it's always straightforward. Of course, with 4 variables, it means 16 rows. But let's do some rearranging here and see what we can accomplish. Remember that you can reorder the hypotheses. The hypotheses are not ordered in any way. You can place them in any order you want. So if we want to try to make a chain out of this, a sorites, the hypotheses are all conditional statements. So it at least reminds us of sorites. Maybe we can rearrange the hypotheses to give that chain-like feature. So S only appears once here. So I will put that at the beginning. S implies R. Then I'd like the next implication to have an antecedent R, and that would be the third one. So S implies R, R implies P, and then P implies not Q. So by rearranging this, we now have that chain-like feature in the hypotheses, and we know that S implies not Q is a valid conclusion. Or a better way to put that, if that's the conclusion, the argument is valid. That's probably what I should have said. Okay. So this is, in fact, an example of a sorites. Okay. And therefore, it is a valid argument. So I think if you look at this again, read it again. A student who studies will not flunk this course. John is very smart. Even smart people must study. Therefore, John will not flunk this course. You would initially say, well, gee, I don't know whether that's valid or not. It sounds a little convoluted. But you now have the techniques available to you to decide one way or the other whether this argument is valid or not. And you have a couple of choices here. One is simply, in any case you need the symbolic form for the argument, but one is simply to construct the truth table and stare at the rows. That doesn't require any thinking. The other is to attempt to rearrange the argument so that it looks like something that you already know is valid, such as modus ponens or sorites. Lewis Carroll was the author of Alice in Wonderland, and he was a great fan of symbolic logic. And he wrote a book entitled Symbolic Logic, and it's still available. You can find it. It's published by Dover. And so you can probably buy it on Amazon if you're interested. In his book, he gave 60 very unusual examples of sorites. So let's take a look at one or two of those. Again, I should re-emphasize that you can reorder the hypotheses of an argument without changing its validity. You can also replace a hypothesis by a logically equivalent statement, and that will not affect the hypothesis, the validity of the argument. And one common use of that is to replace an implication by its contrapositive, which is logically valid to the original. So here is an argument of Lewis Carroll. No ducks waltz. No officers ever decline to waltz. All my poultry are ducks, therefore my poultry are not officers. I told you they were unusual. So for the symbolic form, we let P be ducks, we'll let Q be willing to waltz, R be officers, S be my poultry. So the symbolic form now is no ducks waltz, which means duck implies not willing to waltz. P implies not Q. No officers ever decline to waltz, so officer implies waltz or willing to waltz. All my poultry are ducks, so my poultry implies ducks. And the conclusion is, therefore, my poultry are not officers. S implies not R. Rearranging the order of the premises, we get S implies P, P implies not Q, R implies Q. This does not look like a chain effect here. Pardon the noise, it's my timer. I'm trying to keep these lectures to 50 minutes, but that's a little bit tricky when you're not in a classroom setting where everybody starts to get up and leave, and you have to stop in the middle of a mathematical idea, which is very frustrating. So I'm going to complete this discussion of valid arguments, then I'm going to stop. Now we don't have a complete chain here. We have S implies P, P implies not Q, but then we get stuck here. What we need to make this into a chain of hypotheses, of conditionals, is for the antecedent here to be not Q rather than R. No problem, because R implies Q is logically equivalent to its contrapositive, which is not Q implies not R. So when we make that replacement, the argument now looks like it's a different argument, but it's valid at the same time as the first argument. So if we can show this is valid or invalid, we will know the situation for the original argument. So this, as I said, is a Sorites, and so it's if the conclusion is S implies not R, this becomes valid. Okay, and that's exactly what the conclusion is. So this argument with the replacement of this hypothesis is valid, therefore the original argument is valid. Okay. So if you're ever on the street in a store approached by someone who says, "Excuse me, can you help me with an argument? My friend says no ducks waltz. No officers ever declined to waltz. All my poultry are ducks, and therefore my poultry are not officers. Should I tell him that's a valid argument or not?" You will know what to say. That's only happened to me a couple times. In Lewis Carroll's book, he doesn't give you the conclusions. You are asked to fill in the conclusions. So let's try one of those. All my sons are slim. No child of mine is healthy who takes no exercise. All gluttons who are children of mine are fat. No daughter of mine takes any exercise. What conclusion can we draw from this? What conclusion will provide us with a valid argument? Well, again, we need statement variables. P is son, Q is slim, R is healthy, S is takes exercise, T is glutton. Excuse me. Now, in this argument, Lewis Carroll is talking about his children. So daughter is the same as not son. So daughter can be represented by not P, so we don't have to have a separate variable for daughter. And fat is represented by not Q, not is slim. Okay, so by assigning these statement variables, generally you want to assign as few as possible, we have covered what we need to construct the symbolic form for this argument. P implies Q, not S implies not R, T implies not Q, not P implies not S. And I'll let you look over the argument and make sure that's correct. Now, in attempting to rearrange this to produce the hypotheses of a Sorites, we notice that T appears only once as an antecedent, so maybe that's the way to start. T implies not Q. Okay. The next, there's further rearrangement I've done here. I put P implies Q next because I know what's coming, right? I'm going to replace this by its contrapositive, and that will put a not Q in the antecedent to match this not Q here. Okay? And so that's why the first two are in a reasonable order. And the next two, there's only two possibilities. And I wrote it this way. It becomes a little bit harder to see what's going on, but when you replace P implies Q by not Q implies not P, you'll have a consequent of not P. You want an antecedent here of not P. So that'll continue the chain. And then this will be the fourth one. So I'm going to replace this second one by its contrapositive. And now I have T implies not Q, which implies not P, which implies not S, which implies not R. Okay. This is not, there's no algorithm for doing this. You're going to have to fiddle a little bit to find the right order of things. You could probably write down some rules that will help. The obvious one is if you find a variable appearing only once, it's got to be at the beginning, the first conditional, and it needs to be the antecedent, or it needs to be at the very end as the consequent of the final conditional. In any case, the conclusion here that will make this a Sorites is T implies not R. And that is all my gluttonous children are unhealthy. Okay. All right, so that concludes our discussion of valid arguments.